Hey guys, in today's presentation we are going to learn about the usage of memory in text processing. Before that, let me introduce myself. I'm Sai Krishna. I'm currently pursuing data science bachelor's degree at IERE from section B. So what are the objectives of today's presentation? The first would be introduction to what is text processing. Next, the ambiguity that text processing has. Now, it means that when a computer tries to read the text, there lies a certain vested confusion. Now, how computer is able to overcome that confusion is going to be covered in that section. Next, basic understanding techniques. That is, how computer is able to understand the text. Next, using memory during text processing. So how we are able to use memory during text processing will be covered in that section. So without any further ado, let's start the presentation with introduction. The performance of a natural language processing system should improve as it reads more and more text, but it doesn't happen in most of the programs. Virtually all natural language processing systems suffer from the same flaw regarding text does not make them smarter. They are not able to process text better over time, including text that are similar to those previously read. This is clearly a problem for systems intended as cognitive models since human language performance improves in a domain as knowledge is acquired. It is also troublesome for practical systems since the lack of learning ability requires all the information needed for understanding to be hand-coded by the implementer. Researcher is a language whose language understanding ability will improve as it reads the data, since it will use dynamic memory of examples to resolve ambiguities that would otherwise require ad hoc disambiguation rules. Although researcher is not at a stage where quantitative evaluation of its abilities is useful, the system has been tested on over 130 real 130 real patents abstracts. While not of all these are processed perfectly, many are handled quite well, particularly considering the complex nature of the text. Close analysis of examples indicate that with proper information in memory, most of the abstracts could be processed quite successfully. The, the figure on the screen represents the basic researcher modules. So what are the modules involved in the program called researcher? So this researcher will only read patent abstracts. Its input will be various patent abstracts. That's why at the top we have patent abstracts. Next, it will process the text, then patent abstract representation, then memory update and generalization. So what is happening is it will read the text. If there is any new word that it has, then it will generalize it and store it in the memory. Generalization based memory. Then it will recall the memory and ask whether it has a reference to what we being read. If yes, it will again go to text processing. So to clearly make and to clearly understand what the text is intended to. Intelligent question answering. Now for generalization, we need intelligent question answering, which will be covered in the further section. Right now, researcher is able to read text well because it uses intelligent question answering to remove the ambiguity. Okay. Ambiguity need for memory access. Earlier work on the use of memory in text processing has suggested that memory access might help in allocating resources how and when to apply computational effort, and in identifying the important or interesting part of a text. However, these are imprecise ideas and are difficult to apply. For example, IPP, an earlier program that read, remembered, and generalized from news stories about international terrorism, would know from accessing memory that the destination of a hijacking in a story that began a United 727 en route to Miami was commandeered blank. So we are just given a part of a sentence. Now, how the IPP will react? It will say that it would likely to reach Havana. However, it was not clear how you would use this information. Simply said to Havana, it is quite easy to process this text without the expectation, and memory just provided a redundant cross-check. Providing default information was IPP's main use of memory. Had no destination been mentioned in a Miami-bound hijacking, IPP would have inferred Havana. Means it will not given Havana as an example. So while IPP did in this manner get somewhere smarter as it reads, its improvement was not as great as one would have hoped. We are proposing using memory for understanding as opposed to general semantic information about words or concepts. By memory we mean an appropriately organized knowledge base of detailed information acquired from previously read text. This can involve specific examples as done in researcher and or information generalized from examples. In memory, in our case, how the objects described in patent abstracts are constructed and how their pieces relate to each other. So we are going to use memory so more than the conventional semantic interpretation in order to have a more clear understanding of the objects that are present in the text, and computer is able to read the text more effectively. Moreover, we are going to present questions to the researcher in order to in order to make text disambiguous. And these questions are asked to the memory. Now, while general semantic information is crucial for our conceptual-based understanding methods, in order to resolve many understanding questions, it will be necessary to look at very detailed information. Let's take some examples. Now, there is an example: read or write head touching a disk made from XXX, so on. So this is a sentence from a patent abstract. Now let's see how a researcher would have behaved if it read this sentence. In this example, there is no way to determine whether XXX is the material used for the read or write head or for the disk without knowing something about the objects involved. Different XXX would be analyzed differently. In some cases, a single triple X could lead to different analysis depending upon the state of memory. For example, if triple X was plastic in a sentence, our analysis would depend on what we knew about plastic discs and plastic trees or whiteheads. The resolution of disambiguities such as those in this example and also the next example, that is a floppy J hinged disk support, is an area where we believe memory can be immediately useful in text understanding systems, in addition to supplying default values. While the specific methods described here are for researchers and so are tailored to read patent abstracts, ambiguity is a problem that is suffered by most of the natural language tasks. Our memory-based resolution techniques will be widely applicable throughout the NLP sector. The problem of disambiguation is not a new one. Linguists have looked at problems of ambiguity for many years. One linguistic method to resolve certain ambiguities is the use of semantic constraints. For example, to take an example adapted, suppose we are trying to analyze red castle and determine whether red modifies car or safe. If our definition of red says that it only modifies physical objects, then we can determine the correct modification assuming car is defined as a physical object and sale is known. The application of semantic information, including semantic feature of words to resolve ambiguity, has also been widely used in artificial intelligence research. Constructions similar to those we will be considered. Okay, now disambiguation questions, that is how we are going to remove ambiguity from the text. See, concrete noun phrases in English, that are phrases which describe objects, can have very complex structure. Research emphasis on object description requires detailed attention to the internal structure of noun phrases so that it can identify how the pieces of such phrases are fit together. The questions are based on a functional classification of words but largely involve noun-to-noun situations with or without adjectives and attachment of prepositional and verb phrases. Our proposal for ambiguity resolution is to access memory when object description and complete are completed, and when these object descriptions are being combined, the researcher will perform disambiguation by asking questions of memory. Typically, such processing will take place at syntactic phrase boundaries, although from our point of view this is largely coincidental. Specifically, we have identified a group of very specific ambiguities involving noun groups that we can use researchers' memory to resolve through well-defined questions. What is new is not the specific ambiguities, but the integration of disambiguation questions into conceptual analysis methods and the use of an automatically generated dynamic memory to answer these questions. So let's take some examples and what are the questions the researcher has formed for it. For the example 4, we have object word. The example is an actuator housing. Now, what is the relation between object word 1, that is actuator, and object word 2, housing? Next, the example is a metal drive cover. Does the modifier, that is metal, is applied better to the object word 1, that is drive, or object 2, cover? So like these are examples, and researcher is able to identify the noun to noun objects and file a question or generate a question for the memory in order to effectively read the text. So what are the basic research understanding techniques that the researcher program implement in order to learn to these texts? Researcher process patent abstracts by using basic syntactic tools to identify objects in the ultimate representation and combining these objects by adding appropriate relation to the presentation. The goal of the text interpretation phase is to build up descriptions of objects, including physical and functional relations between various parts of the objects, using a canonical frame-based representation scheme. Let's see an example. An electromagnetic linear actuator for a positioning a transducer. This is a sentence that is read by the researcher. And let's take another example with this of same sentence but of slight difference. An electromagnetic linear actuator that positions a transducer are functional equivalent but involve different syntactic answer. Okay, sorry. So again, the example would be an electromagnetic linear actuator that positions a transducer. Now in the previous example, it was for, but now it is that. We as humans are able to differ, like distinguish that both have the same meaning, so nothing much of a problem. But as we are using syntactic structures in order to understand what the text is, for the researcher, it will cause a major problem. So, researcher also has to come around such problems, and this can be done not solely depending upon the semantic information of the objects, but on the relations between the objects by putting more emphasis on understanding the relations between uh, various objects in the text. So, mimic identification. The noun phrase recognition process involves the same save and skip strategy using a one-word look-ahead process. Researchers says noun phrase words in a stack until the head noun is reached. Then the word I in the stack, then the words in the stack are popped off and used to modify mehmet, indicated by the head noun. Noun group recognition could also be done easily with simple bottom-up syntactic processing. Determining how the words within a simple noun group relate to each other is a problem. Now, for example, in a typical phrase such as a fixed head disk drive assembly, there is no way of knowing whether fixed modifies head, disk, or disk drive or assembly without using the knowledge about the structure of a disk drive. See, the final portion of memory identification invokes checking for anaphoric reference to the object described. Here, the researcher is able to take advantage of some of the arcane nature of patent abstracts. A very strict formalism is used for reference in patents involving the words said and exact repetition of identifying modifiers. Without such formal language, the reference process would be very complicated, and as an abstract can refer to many very or similar objects as it is, we can use a simple reference procedure that avoids many techniques needed for sort text. Now, uh, for integrating memory access with text processing. So, asking the disambiguous question fits nicely with the overall research or text processing algorithm. Researchers save and skip noun group strategy naturally accommodates memory-based disambiguation as the program is processing the items from its short-term memory stack. It keeps track of the identified memos that can be modified, the memos described by the head noun, the most recent noun, and certain intermediate nouns. As researcher continues to work back through the stack, if there is more than one distinct object described in the noun group, memory can be queried to determine in which object new words modify or relate to. Now, using memory during text processing, what are the problems that will arise? When relevant examples are found in the memory, that that too in many numbers, those nearest the top of the generalization hierarchy, that is in the most general object description are used. So if the general disk drive has a read or write head on top of its disk, while a specialized version had it underneath, we would use the on top of relation in resolving disk drive head. Now let's conclude what we have learned. NLP modules, when NLP modules utilize memory to perform even better. Now, researcher is such a module that utilizes memory for disambiguation. It asks questions based on the objects it identified, that to noun phrase in noun to noun phrases to the memory in order to have much more depth information about the text. Thank you for listening.